Today I'm going to talk about the relationship between reduction and the autonomy of the spatial sciences, or what I take to be the same, the autonomy of high-level theories. So I'm sure you have here that according to some authors, there is a tension between the autonomy of high-level theories and the possibility of reducing those theories to more fundamental theories. For example, in the context of philosophy of mind, Fodor says that a law or theory that figures in bona fide empirical explanations, but it is not reducible to a law or theory of physics, is ipso facto autonomous. Also in the context of philosophy of mind, Kim says that the conventional wisdom in philosophy of mind is that psychological states are multiply realized, and that these facts refuse psychological reductionism once and for all. And in the context of philosophy of science, Bob Bateman has recently argued that the multiple realizability argument challenges the reductionist claims by highlighting the autonomy of the high-level explanation from the lower-level, very different micro-based explanations. So these claims raise different questions that I would like to answer in the context of this talk. The first question is, what does it really mean for a high-level theory to be autonomous? So different authors seem to give different definitions of autonomy, but the question is, can we find a general definition of autonomy that describes the sense in which high-level theories are autonomous with respect to lower-level theories? The second question is, what is the relationship between autonomy and multiple realizability? As you saw, many authors associate autonomy with multiple realizability, but does autonomy always mean multiple realizability? And the third question, and what I take to be the most important one, is the autonomy of high-level theory, or the autonomy of the spatial sciences, really in conflict with its reduction to more fundamental theories? So as I said, in the context of this talk, I want to offer an answer to all these three questions. And for that, I will follow this plan. First of all, I will give my own definition of autonomy, and I will compare this definition with standard definitions of autonomy offered in the philosophical literature. Then I will refer to some arguments that some authors have given for the incompatibility between autonomy and reduction. And then I will refute those arguments by looking at two case studies. The first one is the case of critical phenomena, which I will take as a successful case of reduction and autonomy, so in other words, in which reduction and autonomy are combined. And the second is a more controversial case, which is the case of stock market crashes, which is a case in which scientists have neither been able to reduce the phenomena to lower-level theories, nor to demonstrate the autonomy of a phenomena, but it's still an interesting case study because it shows us the importance of having both autonomy and reduction in the scientific practice. And then, on the basis of these two case studies, I will draw some general conclusions about the epistemic roles of autonomy and reduction in science. So now let us start. So in a recent book that I wrote on emergence and reduction, I define autonomy as follows. A high-level theory is strongly autonomous with respect to a lower-level theory, if and only if it describes a behavior that is both robust and universal. On the other hand, a high-level theory is only weakly autonomous with respect to a lower-level theory if it describes a behavior that is either robust or universal, but not both. So as you can see in this definition, the distinction between robustness and universality plays a very important role. So what is this distinction? In a paper that I wrote together with Sean Grip and Karim Thibault, we define robustness as follows. Robustness is the insensitivity of some behavior in a particular type of system to variation of the microscopic detail. So in other words, the behavior of a particular type of system will be robust if it doesn't depend on microscopic details. Examples of robustness that will be relevant in this context are, first of all, the observation that phase transitions in water, for example, when water changes from liquid to gas, doesn't depend on microscopic details. For instance, it can be shown that it doesn't depend on particular microscopic configurations at the molecular level. And also, it can be shown that it doesn't depend on many other microscopic details. So basically, the parameters that matter when water goes from liquid to gas are macroscopic parameters such as temperature. Another example that will be relevant in this talk is the observation that the occurrence of specific crash is robust upon microscopic details, for example, upon different social configurations, and also that it is robust upon specific decisions of individual agents. So now, universality is different. I understand universality as the insensitivity of some behavior to changes in the macroscopic details that characterize the type of systems that are considered. So in other words, a behavior will be universal if the same behavior can be instantiated in different types of systems, like fluids and magnets, or humans and octopus, if you are familiar with that discussion in philosophy of mind. So as you can see, the idea of universality is nothing more than the idea of multiple realizability discussed extensively in the philosophy of mind and in the philosophy of science literature. So as Michael Berry, a physicist, said, universality is the slightly pretentious way in which physicists denote identical behavior in different, and I would add, types of systems. So an example of universality is the observation of that different types of systems, like fluids and ferromagnets, have the same qualitative and quantitative behavior close to a critical phase transition. I will refer to this in detail in the talk. Another example is the observation that different types of crashes, like endogenous and exogenous, and also crashes occurring at different times, exhibit some of the same properties. For example, this sudden drop of prices before the crash occurs. So since this distinction between robustness and universality is going to play such an important role in my argument, I will stress now this distinction with an analogy in art. So if we want to think about universality in art, we can have something like this. So this is a replica of the Mona Lisa, which was done alongside the original one, so in the 16th century. And it is believed that it was done by a student of Leonardo. So since it was done by a student of Leonardo, we can assume that the student used the same technique as Leonardo. But of course, many details in this replica change with respect to the original Mona Lisa. For example, we see a path here that we don't see here. And even if the student might have used the same technique, he uses probably a different pencil and a slightly different mixture of colors. But still, despite these microscopic changes, we can distinguish the same macroscopic properties in both paintings, right? So now, if we want to think about universality in art, we come up with something like this. So this was an actual exhibition at the Louvre for commemorating the 500th anniversary of Leonardo da Vinci's death. And here, 6 different painters were invited to reinterpret the Mona Lisa. So as you see here, different macroscopic details change in all these paintings, so we can consider them to be different types of paintings, but we can recognize the same pattern in all of them. So we can think that this pattern is universal because it is invariant upon changes in different types of paintings. Right? So now that the distinction between robustness and universality is clear, I would like to come back to philosophy. So I am aware that my definition of universality, of autonomy in the sense of universality and robustness is non-standard, but what I like of my definition is that it is more general than other specific definitions discussed in the philosophical literature. For example, Fodor understands universality in the sense of autonomy in the sense of nomological autonomy. He thinks that a high-level theory is autonomous if we are able to formulate a law of this kind at the higher level, in which S1 and S2 are higher level predicates. But it is easy to see that in order to formulate and to find a law of this kind at the higher level, we need these terms to be somehow robust with respect to lower level variables. Otherwise, we will not be able to find a regularity of this kind at the higher level. And the same can be said for the case of causal autonomy. So very recently, Woodward defined autonomy in the sense of causation, and he says that a high-level theory would be autonomous if the upper-level variables are relevant to E, but the variables figuring in lower-level or more fine-grained theories are conditionally relevant to E, given the values of the upper-level variables. So here, again, it is easy to see that in order to have this irrelevance of lower-level variables with respect to upper-level variables, we need the upper-level variables to be robust with respect to lower-level variables. So again, in order to have causal autonomy, we need a sense of robustness. And the same can be said for the case of dynamical autonomy, which Robinson defines as the idea of being able of formulating or finding a higher order differential equation in the higher level theories. And one can also see that my definition of autonomy in the sense of robustness and universality absorbs other definitions of autonomy in the sense of stability. For example, Batterman defines autonomy as follows. He says a macroscopic behavior is autonomous with respect to a microscopic behavior if and only if it is stable under changes in the microscopic details. It is again easy to see that in order to have autonomy in the sense of stability, we need some sort of robustness. So now, before we move on to the arguments for the compatibility between autonomy and reduction, I would like to add some clarification. So in the literature in philosophy of mind and also in philosophy of science, there seems to be a dichotomy between full autonomy, which is the idea that the high-level theory is completely independent upon the low-level theory, or apparent autonomy. So it is believed that if we can show that the high-level theory is to some extent dependent on the low-level theory, then we should conclude that the autonomy is only apparent. So as Katie Robertson has pointed out recently in her work on autonomy, this dichotomy is only an apparent dichotomy, it's a false dichotomy. One can perfectly conceive cases of genuine autonomy which are not equivalent to full autonomy. Cases of genuine autonomy in which the high-level theory does depend to some extent on the low-level theory. And this is exactly how I interpret my notion of strong autonomy. So strong autonomy should not be interpreted as a case of full autonomy. There might be a dependence of the high-level theory upon the low-level theory, but it is still a case of genuine autonomy. And it is this notion of strong autonomy, the one that I will claim to be compatible with reduction. So before I defend my arguments for the compatibility between autonomy and reduction, I want to discuss the arguments that have been given for the incompatibility of autonomy and reduction. So the most important argument for the incompatibility of autonomy and reduction, I think, was given by Fodor in this very famous paper that he published, Special Sciences or the Disunity of Science as a Working Hypothesis. So here he understands autonomy in the sense of multiple realizability. And he says that multiple realizability is incompatible with reduction because multiple realizability doesn't allow us to construct the bridge laws that we would need in order to reduce the high-level theories to the low-level theories. In particular, what he says in this paper is that in order to reduce a high-level theory of this kind, what we need is to construct bridge laws that establish a one-to-one correspondence between the high-level properties and a physical property. And once we do that, once we establish a one-to-one correspondence between the high-level properties with the low-level properties, we need to find a law that establishes the relationship between the low-level properties. So the problem with multiple realizability is that at best, what we have is a relationship between a high-level property and a disjunction of low-level properties, or a disjunction of lower-level realizers. If we think, for example, about the case of money exchange, and if we take the low-level theory to be a physical theory, or physical realizations of this property of money exchange, then we can conceive many, perhaps infinitely many ways in which money exchange is physically realized. So he says that this is problematic, first of all, because it's practically difficult to come up with the bridge law that relates money exchange with all possible physical realizers for money exchange. And he also says that it is implausible that we interpret this disjunction as a law, because the way in which money exchange is realized in the physical world seems to be just a contingent fact, not a law of nature. So the second argument for the incompatibility of autonomy and reduction was put forward by Batterman more recently in this paper, Autonomy of Theories, an Explanatory Problem, and also in recent papers and in a book that he wrote that is called A Middle Way. So he basically said that the problem or the tension of between reductive explanations and autonomy appears because reductive explanations don't help us answering the relevant question that we need to answer when we wonder about the autonomy of high-level theories. So the relevant question here, which he calls the multiple realizability question, is how can it be that systems that are heterogeneous at some micro scale exhibit the same pattern of behavior at the macro scale? So the problem is that reductive explanations, which he takes to be detailed explanations of individual systems, don't help us answering the relevant question, don't help us answering this question. So in the present science, he says, we cannot explain the macroscopic behavior of every individual system on the basis of a single fine-grained description of the system. And even in a perfect science in which we would have a detailed explanation of all macroscopic behavior corresponding to individual systems, we would still, with the help of these detailed explanations, not being able to answer the relevant question. So in order to answer the relevant questions, he says, we need to abstract away. So it seems that the only hope to answer this relevant question, this multiple realizability question, is to consider multi-scale explanations, which are explanations that study a phenomena, but from different scales. And the problem is that these multi-scale explanations, which are intrinsically abstract explanations, is that they should not and they cannot be interpreted as reductive explanations. First of all, because they are not bottom-up derivational explanations, so on the basis of micro-scale explanations, one cannot derive the macro level from the micro level. They normally, in fact, require appealing to features and properties of different mesoscale levels, which actually is in contradiction with the core idea of reductive explanations. And finally, sometimes they even involve the use of ineliminable idealizations, like infinite limits, which block reduction. So what I will do now is try to reply to all these three arguments by looking at the case of critical phenomena. So for the ones that are not philosophers of physics here, I'm sure philosophers of physics have heard this before. In the 40s, physicists found that different systems, so different as neon and oxygen, display exactly the same qualitative and quantitative behavior close to a critical phase transition. In fact, you can see here this graph that appears in a paper by Guggenheim that he published in 1945, the comparison between 8 different types of systems. And you see that these 8 different types of systems display not only the same qualitative behavior close to a critical phase transition, but the same quantitative behavior. So this is a very interesting case of universality or multiple realizability, which I take to be the same. So for many years, physicists were puzzled about this universality exhibit in critical phenomena. And in the 70s, finally, they came up with an explanation of universality. This explanation was elaborated by Wilson and involved the introduction of methods that are called renormalization group methods. So the details of renormalization group methods are very challenging, but one can understand the main idea of renormalization group methods as follows. So what we do in renormalization group methods is to define a transformation that successively coarse grains the system until one reaches a fixed point, which means that applying this transformation doesn't change the system anymore. So at each step of this coarse graining, what one does is to average out degrees of freedom and get rid of irrelevant coupling constants, which are variables that give us detailed information about the system. So the interesting fact is that these methods not only help Wilson to give a prediction of critical phenomena for individual systems, but also help him explain universality, because it was shown that systems that flow towards the same fixed point were systems in the same universality class, which means that were systems that behave in the same way close to a critical point. In a paper that I wrote with Jean Grip and Karim Thibault, which is also a paper that I mentioned before, we showed that this framework helped us demonstrating and explaining a high degree of robustness, because it tells us that most coupling constants, most micro details, if you want, are not important, are irrelevant for the behavior close to a critical point. It also helps us establishing a high degree of universality because it tells us that and helps us explaining why different systems have exactly the same behavior close to the critical point. And we can rely on this demonstration of robustness and universality here because the framework is also physically plausible, which means that we can de-idealize the assumptions involved in this framework. It also has a high degree of comprehensiveness because it captures all the relevant observables here. And it also has a high degree of empirical support because one can contrast the calculations of the critical exponent with actual experiments. And finally, it has a property that we call integration, which means that the theoretical framework for demonstrating robustness and universality is consistent. In this case, integration is maximum because one can show that the theoretical framework for demonstrating universality and robustness is actually the same. So we can confidently say that the theory of critical phenomena is a case of strong autonomy in the sense that I define autonomy. It's a case that demonstrates a high degree of robustness because one can show that the behavior of individual systems, particular types of systems, don't depend on details. And it's also a case that demonstrates a high degree of universality because it demonstrates that different systems will behave exactly the same way close to a critical point. But the question is it also a case of reduction? And I will say yes. So one of the arguments to say that multiple realizability was incompatible with reduction, that is due to Fodor, is that multiple realizability don't help us defining breach laws that would allow a reduction of a high-level theory to a low-level theory. But here, Jeremy Butterfield, following the work by Sober, has said that not even infinite disjunctions are in principle incompatible with the Nagelian model, which is a standard model of reduction in the philosophy of science. But in the case of critical phenomena, we don't even have infinite disjunctions. We can actually, with the help of renormalization group methods, have a very well-defined breach law in which we relate a very abstract power law with power laws that represent particular models that are in the same universality class, like the Ising model, ferromagnet, and the liquid-gas transition. In contrast to Fodor, there are plenty of reasons to interpret this breach law as an empirical law. First of all, we have theoretical arguments that come from renormalization group methods to give a well definition of this breach law. Second, we can also demonstrate empirically and see empirically which systems are in the same universality class. So which systems should belong to this definition. And then the fact that we have a breach law in terms of a disjunction, I don't think should be interpreted as blocking the possibility of reducing a high-level theory to a low-level theory. And here I follow Sober when he said, are we really prepared to say that the truth and lawfulness of the high-level generalization is inexplicable just because the derivation is peppered with the word or? Again, I don't think so. So the second argument given by Bateman was that normally reductive explanations don't help us answering the relevant multiple realizability question, which is how can it be that systems that are heterogeneous at some microscale exhibit the same pattern of behavior at the macro scale? But in this case, renormalization group methods do exactly that. By demonstrating the robustness and the universality of critical phenomena, they precisely help us answering this question. And the reason why different systems behave the same close to the critical point is because one can show that the details that distinguish these systems are irrelevant for the behavior at stake. But someone like Bateman or Mark Wilson would agree with this reply, but they would still insist that renormalization group methods don't constitute reductive explanations. They would think that renormalization group methods explain the universality associated to critical phenomena, but they are not a reductive explanation. In fact, they take reductive explanations to be these unified detailed explanations of individual systems. And they said that renormalization group methods don't correspond to these detailed explanations of individual systems because renormalization group methods intrinsically involve considering different mesoscales at the same time. And they intrinsically involve abstractions and approximations and idealizations. So what I would reply to them is that this definition of reductive explanations as detailed explanations of individual systems is just far too strict. And here I rely on the work done recently by Alex Franklin on autonomy, in which he says that in order for an explanation of universal behavior to count as reductive, the only thing that we need is to explain the stabilities of various features at higher scale, and also to explain why fine-grained detailed explanations fail. Again, renormalization group methods do exactly this. By demonstrating robustness and universality, they explain the stabilities of higher scales, because they tell us why higher scales don't depend on lower scales. And they also explain us why fine-grained detailed explanations fail. And they explain us why we need to abstract away in order to have an explanation of universal behavior. But there are other reasons to consider renormalization group explanations as reductive explanations. First of all, by defining renormalization group transformation, renormalization group explanations successfully establish a connection between lower level theories and high level theories, a connection that it wasn't before. They can confidently tell us that the high level theory is just an abstraction of the low level theory. Moreover, one can interpret this set of mathematical transformations in terms of families of Nagelian reductions, or as I would say, completing the work of Jeremy Butterfield, as a combination of Nagelian reductions plus limiting reductions, because there are many limiting reductions involved here. In contrast to what some authors have said, the infinite limits involved in renormalization group explanations should not be interpreted as ineliminable idealizations. In fact, relying on toy examples and computer simulations, I have showed, together with some colleagues as well, that infinite limits involved in the renormalization group explanation of critical phenomena are completely eliminable. One can perfectly work and calculate and explain universality and calculate the critical exponents without appealing to infinite limits. And finally, it is true that sometimes in order to define a renormalization group transformations, we need empirical input. But as Jeremy Butterfield and Sebastian Rivat and Alexei Greenbaum have pointed out, this appeal to empirical input is not inconsistent or incompatible with Nagelian reduction, because it can take part of the auxiliary assumptions. So I admit that I could give an entire 1-hour talk on this slide. There are many subtlenesses here that we might discuss in the Q&A, or that you might read when you read all this work. But I want you to accept my arguments for a moment. So the thing is that if we accept all these arguments, then we can, which I think are true, I think we can conclusively say that critical phenomena are a successful case of autonomy and reduction. But now, let us look at a more controversial, but maybe also a more interesting case, which is the case of stock market crashes. You all know that stock market crashes are these undesirable events that happen when prices suddenly go down, creating chaos in the economy and in our everyday life as well. So for many years, economists and other scientists have been trying to find a model that can account and predict these extreme events. But mainstream models, which are normally based on normal distributions, have dramatically failed in making predictions of stock market crashes, as you might know. So in this context in which standard models fail in predicting stock market crashes, Johansen, Leroy, and Sornet suggested an alternative model, which is part of econophysics. So basically what they did was to build an analogy between critical phase transitions and the occurrence of stock market crashes, and they motivate the use of physics tools by this analogy, they motivate the use of physics tools for the explanation of stock market crashes. So by doing that, they aim to capture stylized facts or regularities that characterize the occurrence of stock market crashes. They also wanted to provide a microscopic foundation for stock market crashes. They wanted to give a microscopic explanation of stock market crashes. And then finally also wanted to predict extreme events, again, like stock market crashes. So the analogy that is a starting point of this model, is this analogy between phase transitions in physics and what happens in the stock market. So in physics, magnetic materials can go from a paramagnetic phase in which spins are randomized to a phase that is called ferromagnetic phase in which spontaneous magnetization appears. So this transition doesn't occur, of course, this transition occurs at a certain temperature that is called the critical temperature. Now, they built an analogy between this behavior of phase transitions in magnetic materials with the behavior in economics. So they observed that in the stock market could go from a fundamental phase in which prices follow random walks to a phase in which prices spontaneously increase, which is the bubble, which, as we know, is almost in all cases what antecedes a stock market crash. Of course, this transition doesn't happen at a particular temperature, but it happens at a particular time that is called the critical time in this model. So based on this analogy, they postulate a macroscopic model, which is the macroscopic level of this JLS model, in which they establish the relationship between the price returns and this age that is called the hazard rate. That is defined as the probability per unit time that the crash will happen tomorrow, given that it hasn't happened yet. And now, relying again on the analogy with physics, they gave a meaning to this hazard rate. And they posit that the hazard rate would behave in the same way as the magnetic susceptibility, which in physics tell us something about the tendency of the system to change its overall state under a very small perturbation. So they posit that the hazard rate, which tells us information about the probability of a crash, behaved in the same way as the magnetic susceptibility. Since the magnetic susceptibility in physics follows a power law, they assume that the hazard rate also follows a power law. Since the magnetic susceptibility diverges at the critical point, they postulate that the hazard rate would diverge when the crash occurs. And now, by using a little bit of calibration with actual models and actual data, they postulate further that this critical exponent corresponds to a complex number, which gives rise to this new term here that represents log periodic oscillations. Interestingly, they showed by retrodictions and by analyzing certain models that these log periodic oscillations, for example, for the crash of 1987, could be observed with a naked eye, like this. This is the curve representing log periodic oscillation. So the model at the beginning sounded implausible, but the more one reads on this model, the more plausible it sounds, and it looks to some extent also empirically correct. But it has some limitations, and the limitations are precisely related with the incapacity of the model of demonstrating strong autonomy in the sense of robustness and universality. So the question is, does the JLS model succeed in demonstrating the universality and robustness of stock market crashes? So in a paper, this is very small, but I hope you can read a little, at least the title. In a paper that I wrote with Jennifer June and Jim Wetherell, we analyzed different aspects of this JLS model, and in particular, we analyzed to what extent it helped us demonstrate the universality and robustness of stock market crashes. And we arrive at this conclusion. So the model succeeds in demonstrating a high degree of robustness. So the model is insensitive with respect to many different details associated to particular types of crashes. But the model fails in demonstrating a high degree of universality. So the degree of universality that we can imply from this model is only low to moderate. Apart from this, the physical plausibility is only moderate, comprehensiveness is low, and empirical support is also moderate. So let me go into details of these properties. So the model demonstrates a high robustness associated to stock market crashes because it doesn't depend on specific configurations of agents. So it is robust upon different types of networks. And it is also robust upon different types of interactions. So we can consider in our model that the agent interacts with two neighbors, but we can also consider that the agent interacts with infinitely many neighbors at the same time, and the results are the same. It is also robust because it associates the phenomenon of stock market crashes with scale invariant behavior, which means that the model is not very sensitive to a particular scale that we study. but it fails to demonstrate a high degree of universality. So one of the things that Johansen, Leroy, and Sornet wanted with these models was to show that the values of the critical exponents for different crashes were comparable. And what they actually wanted to do originally was to show that the critical exponents had the same values as existing models of physics. But they fail on doing so. So we stress this point in our paper, and we also relied on the work by some econophysicists. For example, the work done by Bodmer and Meister. So Bodmer and Meister said, by analyzing 88 years of the Dow Jones, that almost every crash seemed to be in a different universality class. So every crash has a different value of the critical exponent. It is not possible to have well-defined universality class when we look at the case of stock market crashes. This has terrible consequences for the predictive power of the model that I will mention in a bit. But before, let me refer to the other properties that we analyzed. So the physical plausibility in this model is only moderate because one can justify some idealizations, for example, scale invariance and the limits that are involved, even infinite limits. But there are other idealizations that are still controversial, like locality, and this is something that I'm developing now in a new work with Jennifer June. The assumption of locality in this model is very hard to justify. I can explain you that in the Q&A or later. The degree of comprehensiveness is very low because we focus only on two observables at the macroscopic level, which is price and hazard rate, and we leave aside other factors that might matter for the occurrence of stock market crashes. Also at the microscopic level is low because we focus only on 2 degrees of freedom of agents, which is buy and sell, but again, there might be other degrees of freedom that are relevant here. The empirical support, if we want to be generous, it's moderate because it relies only on retrodictions and it doesn't make any particular, so no predictions have been tested here. And integration, which is the idea that the theoretical framework for robustness and universality is consistent, is also moderate because it is not inconsistent, but in contrast to the Wilsonian case, it is not the same. We use entirely different theoretical arguments for demonstrating robustness and universality. So the consequences of this result are important for the validity and especially for the predictive power of the model. In particular, the fact that they didn't find close values of the critical exponents in the stock market crashes that, the fact that they didn't succeed in establishing that the critical values associated to stock market crashes were close to the critical exponents of existing models means that we cannot use existing models in physics, like the Ising model, in order to make particular predictions of stock market crashes. Apart from that, the fact that the critical exponents of all crashes seem to be different means that there is not even hope that we can build a particular idealized model which is intrinsic to economics but help us making quantitative predictions. But still, the fact that the model is highly robust and shows a high degree of robustness associated to stock market crashes, and also that it shows to some extent a moderate degree of universality in the sense that different crashes can be associated to log periodic oscillations, means, for us at least, that we can use the model to make qualitative predictions, which means that if we observe a log periodic oscillations, it means that roughly the stock market crash might come soon. And it also justifies maybe the fact that we can use abstract models to give qualitative explanations. So we might make qualitative predictions and qualitative explanations with abstract models because we have demonstrated robustness and a moderate degree of universality. But because there is no strong sense of universality here, we cannot use abstract models to make quantitative predictions, which is something that JLS wanted at the beginning. Now, I will also emphasize that this attempt of demonstrating that stock market crashes are autonomous, is not at all in tension with the idea of reducing the behavior of stock market crashes to lower level theories. In fact, in the same model, the authors try to give a reductive explanation of stock market crashes. The extent to which they succeed is controversial, but at least it is important to know that alongside demonstrating autonomy, they wanted to demonstrate the reduction of stock market crashes to lower level theories. And one can see that there are reductive aspects associated to the JLS model. In particular, they associate certain breach laws, so one can associate the hazard rate in economics with a particular quantity in physics, that is the magnetic susceptibility. Also, the fact that they postulate that the critical exponents are complex numbers help us associate in the occurrence of a crash to a family of networks characterized by hierarchical lattices like beta lattice. And finally, and I think the most reductive aspect of the model, is that it associates the occurrence of a stock market crash, which in principle is a macroscopic phenomena, with a microscopic explanation. So in fact, the model suggests that it is local imitation between traders, noisy and rational traders, which cascades through the scales into large-scale coordination, the main cause of a crash. So in this sense, we can see that the model is giving us a reductive explanation of stock market crashes to some extent. And that the project of demonstrating autonomy was not at all in tension with the project of reducing the stock market crash, the occurrence of stock market crashes to lower level laws. So now I think based on these cases, we can learn something about the epistemic roles of autonomy and reduction, and we could also stress that autonomy and reduction should not be considered as incompatible. So in physics, I only talk about the case of critical phenomena, but we can make a more general claim. So there is a very important discussion in physics and philosophy of physics about effective field theories, which are defined as theories that effectively capture everything what is relevant at a given scale. It is easy to see that in order to establish that a theory should be interpreted as an effective field theory, we need to demonstrate that the theory is autonomous in the strong sense, that it's not only robust, but also universal, that the same theory can be applied to different types of systems. Autonomy tells us something also about the scope of the theory. In fact, proving that a theory is universal assures us that we can apply the theory to different types of systems within the same universality class. Also, it tells us something about the resilience of the theory. In fact, demonstrating that a theory is robust, which means at least weakly autonomous, means that it will not break down by modifying microscopic details, that we can rely on our calculations, that our calculations are not too sensitive to microscopic details. And finally, especially if we think about the case of stock market crashes, proving that a theory is universal can also help us justify the use of idealized models, not only for giving qualitative explanations of the phenomena, but also for making quantitative predictions, which is what fails in the case of the JLS model. And now if we think about the roles, the epistemic roles of reduction, we will realize that these roles are not at all in tension with the roles of autonomy. In fact, one of the roles of reduction is when we reduce a theory to another, is to justify the success of the previous theory. For example, when we succeed in reducing Newtonian theory to Einstein theory, we could justify why Newtonian theory was so successful in the past. Another role, which was stressed in a different context today by Sam Fletcher in his talk, is that the reduction of a theory to another can help us as a heuristic guide for the construction of the new theory. This is especially relevant if we look at contemporary physics in the case of quantum gravity. Finally, we have confirmation. So reducing a theory to another can help us confirming the new theory. So the fact that the reducing theory can recover the successful predictions of the old theory give a degree of confirmation to the new theory. Also, we have explanation. Sometimes by reducing a theory to another, we succeed in explaining a phenomenon that cannot be only explained on the basis of the reduced theory or the high-level theory, which is the case of critical phenomena and the explanation of universal behavior. And finally, but this is not at all the only goal of reduction, we have ontological economy. When we reduce a high-level theory to a low-level theory, we might conclude that the ontology of the high-level theory is nothing over and above the ontology of the low-level theory. So now let me conclude, because I think I'm almost on time, a little bit past the time. So at the beginning, I posed 3 questions that I think I have given an answer to. The first was, what does it mean for high-level theory to be autonomous with respect to a low-level theory? And I came up with a very general, what I take to be a very general definition of autonomy, which is that it means that it describes a behavior that is robust and universal with respect to the low-level theory. The second question was, what is the relationship between autonomy and multiple realizability? And I conclude that multiple realizability, in the sense of universality, implies autonomy, but the converse doesn't hold. So we can think about cases like the stock market case in which we have robustness, but we don't have universality in a strong sense. And finally, is the autonomy of high-level theories really in conflict with its reduction to more fundamental theories? And here I will answer with an emphatic no. Both concepts are compatible, and both concepts can contribute to scientific progress. So now, to finish, what I suggest is that in the philosophy of physics, and also in general in the philosophy of science, we move on from this representation of autonomy and reduction as being in tension with each other, in which only one of them survives. This is a painting by Goya called Duelo a Garrotazos, to this other representation of the relationship between autonomy and reduction, in which they both live happily together and even help each other out.